Welcome to the lecture series on mathematical methods and applications. So, let us discuss some more applications of Fourier transforms. So, we have already discussed some applications in the last lectures, Fourier series, Fourier integrals and Fourier transforms. Now this we have already discussed that how we can find out Fourier derivative of sine or cosine transform derivatives. This we have already discussed, that if we want to find out Fourier cosine of f dash x, so that will be nothing but omega Fourier sine of f x minus f 0, and similarly if you want to find out Fourier sine of f dash x, it will be nothing but minus omega Fourier cosine of f x. So, when you replace f by f dash in the first expression and f by f dash in the second expression, you will get back to these two expressions. So, what are these two expressions? So, let us this we have already derived in the last lectures. So, what is Fourier cosine of f double dash x? Fourier cosine of double dash will be nothing but this we have already derived, it is minus omega square Fourier cosine of f x minus f dash 0, and Fourier sine of f double dash x is nothing but omega square Fourier sine of f x, okay. It is minus omega square Fourier sine of this plus omega f 0. So, these results we have already discussed in the last lectures. Now, how they are important and why I am discussing these things over here, let us see. Now, in this problem, solve the equation ut equal to del u by del t is equal to 2 del square u by del x square. This equation we have to solve. Now, x is greater than 0 and t is greater than 0. Now, x is varying from 0 to infinity. So, that means we have either to apply Fourier cosine or Fourier sine transform, because if this x is not varying from minus infinity to plus infinity. If x is varying, if any one of the variable is varying from minus infinity to plus infinity, then we have to apply Fourier transform. But this x is varying only in half range from 0 to infinity. So, that means we have to apply either Fourier cosine or Fourier sine, okay. Now which we have to apply Fourier sine or cosine, how we will decide? We will decide by seeing the conditions. If we apply Fourier cosine in f double dash, here f double dash is this term, we are applying Fourier transform, Fourier sine or cosine transform with respect to x, okay. So, we have a double derivative. So, when we have a double derivative, we apply suppose Fourier cosine. So, in this we need f dash 0. So, here we need del u by del x, at t equal to 0, at x equal to 0, sorry, okay. We need the derivative condition. So, which is not here. It is only u equal to 0 when x equal to 0, the first condition. So, if we now observe Fourier sine transform, so there we need only f 0, okay, when x is 0, okay. So, in this way we conclude that we have to apply Fourier sine transform in this expression, okay. So, basically whenever we have a half range, we have to apply either Fourier sine or Fourier cosine. When the initial conditions when in the initial condition we have the partial derivative at x equal to 0, then we have to apply Fourier cosine, otherwise we have to apply Fourier sine transform. So, in this particular problem we have to apply Fourier sine transform. So, take Fourier sine transform both the sides, because we have the condition of when x equal to 0, u equal to 0. If we have derivative condition at x equal to 0, then we apply Fourier cosine transform. Now, take Fourier sine transform both the sides. What will be the Fourier sine transform of del u by del t? It will be nothing but 0 to infinity del u by del t of sine omega x into d omega. Okay. So, that will be nothing but d by dt, because this term is free from t. So, 0 to infinity u into sine omega x into d omega, which is nothing but d by dt of Fourier sine transform of u x t. Okay. So, now when you take Fourier sine transform both the sides, it will be nothing but d by dt of Fourier sine transform of u x t, which is equal to 2 times minus omega square. Apply this result. So, Fourier transform of sine transform of u x t plus omega into 0, because u is 0 when x is 0. Now, let Fourier sine transform of u x t as, suppose you take it for f of s, it is omega t. Okay. Because we are applying Fourier transform with respect to x. So, that is, it is d upon f s upon dt, which is minus minus plus 2 omega square f s, which is equals to 0. So, that implies d f s upon f s is equals to minus 2 omega square dt. When we integrate both sides, f s is nothing but you obtain as k times e की power minus 2 omega square t. So, again this k will be nothing but function of omega. So, now we have the next condition, where when t equal to 0, u equal to e की power minus x, we have this condition. So, now apply this condition over here. So, what we obtain? So, u x 0 is e की power minus x. So, apply Fourier sine transform both the sides. So, Fourier sine transform of this expression will be nothing but Fourier sine transform of e की power minus x, which is nothing but 0 to infinity e की power minus x sine omega x into d omega into dx, sorry, it will be dx. So, it will be equal to 1 upon 1 plus omega square, and it is minus e की power minus x. You integrate by parts, and minus e की power minus x omega cos omega x from 0 to infinity. So, this is nothing but 1 upon 1 plus omega square. So, when x is tend to infinity, both will tend to 0. When x is tend to 0, it will 0, it will be nothing but minus minus plus, it is omega. So, that will be nothing but omega upon 1 plus omega square. Okay. Now, when you take t equal to 0 here, so Fourier sine transform of u x 0 will be nothing but f s omega 0. So, this is nothing but basically f s omega 0. So, when you take f s omega 0 here, f s, when you substitute t equal to 0 here basically, so it will be k omega, and k omega is nothing but from here will be nothing but omega upon 1 plus omega square. Okay. So, therefore, what will be f s? F s omega t, it will be omega upon 1 plus omega square e की power minus 2 omega square t. Now, take inverse Fourier sine transform both the side to find out the solution. So, this implies u x t will be nothing but 2 upon pi integral 0 to infinity omega upon 1 plus omega square e की power minus 2 omega square t, and it is sine omega x d omega. So, this will be the final solution of this problem. Okay. So, here is a solution, the same solution I have discussed here. So, this is a solution 2 upon pi 0 to infinity omega upon 1 plus omega square e power minus 2 omega square t sin omega x into d omega. Okay. Now, the next problem it is again in half range. Now, here the half range is in y is varying from 0 to infinity. So, that means we have to apply Fourier sine or Fourier cosine transform with respect to y. First we have to decide that for which variable we have to apply Fourier sine or cosine transform, and that depends on the range. Here x is in 0 to L and y is varying from 0 to infinity. So, we have to apply Fourier sine or cosine transform with respect to y, number 1. Number 2, we have to apply Fourier sine or Fourier cosine, that will decide by the conditions. Now, here we will apply Fourier sine or cosine transform with respect to y, and the partial derivative with respect to y when y is 0, it is given to us. That means we will apply Fourier cosine transform here, because when you see this expression in Fourier cosine transform, the second derivative, here we have the derivative at x equal to 0. Okay. So, that means we have to apply Fourier cosine transform when we have the derivative term in the initial conditions, okay. So, here del u by del y at y equal to 0 is given, that means we have to apply Fourier cosine transform. So, now in this problem apply Fourier cosine transform both the sides. So, what is the problem basically? Now, the problem here is del square u upon del x square plus del square u upon del y square equal to 0. So, you will apply Fourier cosine transform, that is clear, and with respect to variable y, that you have to apply. Apply Fourier cosine transform with respect to y. So, what we will obtain? So, x will be free. So, it is d square f upon dx square. Now, let us suppose Fourier cosine transform of uxt, uxy will be nothing but, suppose it is fc x omega, because we are applying with respect to y. Okay. So, x we will treat as it is. So, it will be f c x omega plus. Now, to find out now when we apply Fourier cosine transform here, so we will apply that result that will be nothing, that is nothing but minus omega square Fourier sine cosine transform of x omega plus and minus it is del u by del y when y equal to at x comma 0 equal to 0. Okay. This condition we have applied for Fourier cosine transform. So, what we obtain finally? Oh, sorry. So, basically now this term is 0. So, what we obtain? D square fc upon dx square minus omega square fc will be 0, because this is 0. Okay. So, this gives d square minus omega square fc is equal to 0, where d is nothing but d by dx. So, fc will be nothing but c1 e ki power, or you can break in terms of hyperbolic functions. So, it is sine hyperbolic omega x, okay, plus c2 sine hyperbolic omega y. And again c1 and c2 are the arbitrary function and fc is a function of x and omega. So, c1 and c2 are the nothing but functions of omega. Okay. So, it is c1 sine hyperbolic omega x and okay, it is sorry it is cos. Okay. So, it is cos hyperbolic omega y. Now, use the initial use the conditions. Conditions are u0 y equal to e ki power minus 2y is given to you. Okay. you apply Fourier cosine transform both the sides. So, it is Fourier cosine transform of e ki power minus 2y. So, which is given as 0 to infinity e ki power minus 2y, and it is cos omega y into dy. So, when you integrate it, what we will obtain? It is 1 upon 4 plus omega square, and again you integrate, so it is minus 2 minus 2y, it is cos omega y minus minus plus e ki power minus 2y omega sine omega y from 0 to infinity. At infinity both will tend to 0, and at 0 this is 0 and this will be 1 and minus minus plus. So, it is 2 upon 4 plus omega square. So, this we will obtain here as the Fourier cosine transform of this term, and again when you substitute x equal to 0 both the sides, so this will be nothing but is equal to f c of 0 omega. So, when you take f c of 0 omega here, f c of 0 omega here, so sine hyperbolic 0 is 0 and cos hyperbolic 0 is 1. So, it is nothing but C2. Okay. It is nothing but it is also actually x, it is also x. Okay. You are putting x equal to 0. So, when you put x equal to 0, it is 0 and it is 1. So, it is C2, and C2 will be nothing but 2 upon 4 plus omega square. Okay. So, in this way C2 can be obtained. Now, for C1 we apply another condition. Another condition is u at Ly is 0. Now, again take Fourier cosine transform both the sides. So, Fourier cosine transform of u Ly will be nothing but Fourier cosine transform of 0, which is nothing but 0. So, and this is also equal to, when you substitute x equal to L both the sides, this is nothing but f c L omega. So, when you find f c L omega from here, f c L omega, so that will be nothing but C1 sine hyperbolic omega L plus C2 sine C2 cos hyperbolic omega L, which is equal to 0 from here. Now, now we know C2, C1 can be find out. So, what will be C1? C1 will be nothing but minus C2 cos hyperbolic WL upon sine hyperbolic WL, and C2 is nothing but this term. So, it is minus 2 upon 4 plus omega square into cos hyperbolic omega L upon sine hyperbolic omega L. So, in this way once we obtain C1 and C2, which is here, then the only thing is you take inverse Fourier cosine transform both the sides to find out the final solution. Okay, that is the only thing remain now. So, what is f c omega t? F c omega t here is nothing but, okay, f c x omega, sorry, because f c is a function of x and omega. So, x and omega is nothing but C1 sine hyperbolic omega x plus C2 cos hyperbolic omega x, where C1 and C2 are given by these two expressions. So, take the inverse cosine transform both the sides. So, u x y will be nothing but 2 upon pi integral 0 to infinity, and that will be f c x omega into e ki power eta omega y into d omega. So, that will be 2 upon pi integral 0 to infinity, and f c is nothing but C1 times, C1 is this term. So, this is minus 2 upon 4 plus omega square cos hyperbolic omega L upon sine hyperbolic omega L, C1 is this term, into sine hyperbolic omega x, okay, and plus C2, C2 is 2 upon 4 plus omega square into cos hyperbolic omega x, and whole multiplied by e की power eta omega y into d omega. So, we can easily simplify this expression, and that will give the final solution of final solution u x y, which is a solution of this partial differential equation. Okay. Which is a solution of this partial differential equation. Okay. So, hence we can solve such type of problems. Okay. So, whenever the half range is given to us, you first make sure that with respect to which variable you have to apply Fourier transform x or y, and that will be decided by the conditions given to us. Okay. So, you apply either Fourier sine or Fourier cosine transforms, and for finding the arbitrary constants C1 and C2, you have the conditions given in the problem, and finally take initial sine or cosine transform to find out the final solution of the given partial differential equation. Now, so this is what I have done here also. This is when you simplify this expression, so we will get this form of answer. This one can easily solve. Okay. So, this is the final answer which we can obtain after solving this. Okay. Okay, it is okay. Sorry, it is one thing I have missed here. It is not e की power eta y. It is basically because we are taking inverse cosine transform. It will be nothing but cos omega y, and it is dy. Okay, d omega. So, similarly it is not it will be cos omega y into dy into d omega, because we are taking inverse Fourier cosine transform. It will be cosine term will be here. Okay. So, that we have missed. So, in this way we will get the final answer. Okay. Now, the last problem, the equation for the vibration of the string is given as this, and initially the string is at rest and the initial displacement is f x. Now, here x is ranging from minus to plus infinity. So, that means we have to apply Fourier transform. Okay. So, and initially string is at rest. These are the conditions given to us. So, simply apply Fourier transform both the sides to solve this problem. So, what is the condition? What is the problem? Del square u upon del t square is equals to c square del square u upon del x square. Okay. And initially the infinite string is at rest. So, that means del by del t of u at x comma 0 is 0, and initial displacement is f x. That means x comma 0 is f x. So, these are the conditions given to you, and x is varying from minus to plus infinity. You have to solve this equation. So, again we will apply the Fourier transform technique. So, you will take Fourier transform both the sides with respect to x, okay, because x is varying from minus to plus infinity. So, that means it is d square upon dt square of f, which is equals to c square eta omega square f, where f is nothing but Fourier transform of u x t, which is a function of basically omega and t. Okay. So, when you simplify this to d square f upon dt square, and it is minus 1, so it is plus c square omega square f equal to 0. So, it is d square plus c square omega square into f equal to 0. So, where d is nothing but d by dt. So, when you simplify this, so f we can obtain as c1 e की power, oh it is cos, because so it is cos c omega t plus c2 sin c omega t. Again c1 and c2 are the functions of omega. Okay. Now, we will apply these conditions. So, we will take the first condition is del u upon del t at x comma 0 is 0. When you take Fourier transform both the sides of this expression, we will obtain Fourier transform of del u by del t at x comma 0 is 0. So, that means d by dt of capital F at x comma 0 is 0. And capital F is nothing but Fourier transform of u x t. Okay, it is Fourier transform of u x t. So, that means when you take d by f by dt, that is 0 at t equal to 0. So, when you apply this condition over here, so the derivative of this will be sine, minus sine. Okay, when t equal to 0, it will be 0, and it will be cos. When t equal to 0, that will be 1. So, we will left with C2 C omega, which is C2 C omega, which is equal to 0. Okay, C2 C omega, which is equal to 0. So, this implies, of course, this implies C2 equal to 0, because C1 C and omega are constant. So, C can't be 0 and omega can't be 0, C2 is the only thing which can be 0. So, F is nothing but C1 cos C omega t. Okay. Now, we have one more condition to find out the value of C1, that is u x 0 equal to f x. Okay. Now u x 0 is f x. So, take Fourier transform both the sides. So, Fourier transform of u x 0 will be nothing but Fourier transform of f x, and that will be nothing but minus v plus infinity f x into e की power minus eta omega x into d omega into dx, sorry. So, that will be nothing but f of, because you are putting t equal to 0, so that will be O f omega 0. So, when you take f omega 0, so that will be C1, and that C1 will be nothing but this expression. So, that will be nothing but minus v plus infinity f x e की power minus eta omega x into dx. Okay. So, now we have the value of C1 and C2 in our hand. So, we will simply take inverse Fourier transform to find out the final solution. So, what is f? F is nothing but C1 cos C omega t, where C is given by this expression. Take inverse Fourier transform both the sides. So, it is u x t will be nothing but 1 upon 2 pi integral minus v plus infinity f omega t e की power eta omega x into d omega. That will give the final answer. It is nothing but 1 upon 2 pi integral minus v plus infinity, and f omega t is C1 into cos C omega t, and C1 is given by this expression. So, we can substitute C1 also. It is f xi e की power minus eta omega xi and cos C omega t e की power eta omega x d xi d omega. Okay. So, that will be here. Now, when you further simplify it, so it is 1 upon 2 pi integral minus 1 plus infinity integral minus 1 plus infinity f xi e की power minus eta xi minus x into omega cos C omega t into d xi into d omega. So, again when you write e की power minus eta theta as cos theta minus eta sin theta, then cos theta will contain omega, which is even in omega. It is also even in omega, even into even remain even. However, when you have a sine term, okay, now this can be written as cos omega xi minus x minus eta sin omega xi minus x, and this into this is an even function in omega, and this into this is an odd function in omega. So, this will be 0 in terms of omega. So, we will left with only one term, that is 1 upon pi integral minus mu plus infinity f xi cos omega xi minus x cos c omega t d xi into d omega. So, that will be the final solution of the given differential equation. So, in this way we can solve several problems, several partial differential equations using Fourier series, Fourier integrals or Fourier transforms. So, I hope in this course you have learned lot of things about mathematical methods, lot of techniques to solve ordinary differential equation, partial differential equation, Laplace transforms, its applications, Fourier series, Fourier transform and Fourier integrals, their applications, that all we have seen. So, I hope you might have enjoyed the course. So, I wish you all the best for your bright career ahead. Thank you very much.